Right, so let's continue with that. So far what we were mostly interested is, and the way we said OT systems are different from IT systems, because even if your data is slightly malicious, if you're sending a malicious command, that might not impact the system. Yeah. So for that one, we run the system. We try to pass that behavior, and try to understand what will happen if we allow this kind of data manipulation or this kind of command injection to the system, and so on. Now, when the operator sends commands at substation to control something, to opening circuit breaker, closing circuit breaker, and so on, they generally, there's no authentication, there's no security in that. Yeah, there's no way you could verify whether this command is legitimate or malicious, unless you simulate or unless you pass and see how it's going to work. So we also look into understand what kind of signature, what kind of security practices that we can build in that can help us understand these things. So we explored something called efficient signature scheme. So we also did something for bad data injections. So how you develop a key in a more dynamic environment. So let's say, as I said, there are situations where we cannot have encryption because data need to be sent in few milliseconds, or sometimes the devices that are handling data are not good enough in terms of computational power. So you can't have traditional encryption and so on. But what we can have is, and the way the concept was is based on the way your wireless system works. Yeah. So if it is sending 100 packets, 1,000 packets, out of it some packet drops, and most of the packet reaches to there. So you can derive. So we wanted to understand if the system is under attack, can we apply some kind of dynamic security to it? If you get a sense the system is under attack, we apply certain security control, and as things normal, you take out that control. Yeah. So that might, in that situation, the system might be a bit slow. You can compromise towards efficiency, but then you can improve security of it. Right. So we developed a method where we were able to generate keys dynamically every few minutes, and also the fact even if your system is compromised, even that key is compromised, the system generates new key in every few minutes. Yeah, automatically. So in some way it can handle the situation even if one of the keys compromised, doesn't have impact on the future and previous communications. So again, I'm not talking about that part, but we are talking the other part where how can we ensure and how can we understand the command is being sent are the legitimate ones. And if somebody is sending a malicious command, we should have in place something to detect it, to understand this seems to be a malicious command. So again, we pick up the traditional typical scenario as we see this: power generation, transmission, distribution, homes, businesses, and so on. You got control center, you got SCADA system, the servers, and so on. And then you are receiving data through RTU, aggregator, and so on. And let's say somebody sends a command at the substation to open one of the circuit breaker for the generator. And we are not sure whether this is a legitimate or a malicious command. So what we're going to do is try understand the system first. So we talk about IEC 61850 the other day. There's another standard is called IEC 60870 that reflects in terms of how you can monitor, control communication, telecontrol in terms of communication protocols, and it's more around telecommunications. So as we know, the substation can send, and it does send, unicast, multicast, broadcast communication depending on system requirement. We talk about the other day different three types of protocols. We talk about public subscriber model. How does it work? Yeah. So there are topics in the system. Topic means there could be different type of data. You have publishers who publish this data. So there are devices, systems that are generating data, different type of data. There are subscribers, there are devices that are collecting that data or need that data to process it. So in a way, this makes the whole process more automated. Whenever there's a topic, whenever they got data, they publish it, and then devices who need data, they kind of subscribe, so they automatically get a notification, the data is available, you just fetch it, and so on. So this standard, so they again it's in 5 parts, so 1 to 5, and they are using a standard asynchronous serial telecontrol channel interface between DTE and DCE. Yeah, so DTE, example of DTE is, for example, laptop, mobile phone, which are more terminal equipment, end equipment, right? And you might have data circuit terminating, which are the intermediate equipment part of the system, maybe switches, routers, all those things. The devices which are part of the network, intermediate devices, but then there might be some end devices, maybe a laptop where you are looking at your screen, everything. So that those are the example of DTE, terminal equipment. So this particular protocol says is based on enhanced performance architecture that support physical data link and application layer of protocol, not everything else. But if you need to use TCP/IP, you can have the same serial frame to use it. This protocol also supports, since the standard is kind of support DNP3, which is distributed network protocol. In the US, we've seen like how does it look like. So if you are in the European country, we do use Modbus protocol most of the time. And if you are in America, in the US, they do use distributed network protocol. Again, DNP3, there were several vulnerabilities in DNP3. They come up with the kind of improved version of DNP3 that has some level of security in it, which is a good practice. Now what we want is to try understand how we can send a legitimate command. Second, whenever we need to send alert messages and some control messages, we also wanted to know no one can fabricate those kind of messages that can create panic. Yeah, if you got a message saying this part of the building got fire, please, vacate this place. People will in a hurry to vacate it. That might not be true, right? So there are 2 kind of node we are talking about. One is supervisory node, one is control node. Supervisory node, the system that are supervised, controlling the system, and controlling node basically the node which are part of the system. So example control nodes could be your RTU, your IEDs, smart meters, and so on, and supervisory may be more on SCADA system and other systems at control center. The operator at control center is responsible for making decisions based on the operating conditions. You need to understand what are the operating system, what is the demand and supply at this point of time, right? And in order to manage this so that the lines don't overload, the equipment don't kind of broken down and so on, in order to maintain everything, you have to make certain decisions after every some time. So you collect data, processes, understand what's wrong in the system, and then you might manage it in somehow. So we assuming here there's an adversary that can alter the power system dynamics by maliciously but yet valid commands over the network. Someone can send a command to open or detach a generator that might have a consequence on the real system. So again, we were also saying whenever we develop this kind of thing, we need to ensure the overheads are as low as possible. We should be picking some kind of attack that the system can defeat against, for example, repudiation attack, impersonation attack, replay attacks, insider attacks. And the way we should be designing our system in such a way, for example, a module at supervisory node generate a fresh command and send it to the respective control node with fresh information. So you need to check what is the freshness here. Module at control center is activated immediately after receiving a command from the supervisory node, which could verify whether the received command is legitimate or not. Now, when we say control node, supervisory node, whenever we need to send a command, this will always be done by the control center at substation, not the other way. Whenever there's a need of data exchange, polling request always comes from control center to substation saying send your data. Yeah. So the data comes from substation to control center. Commands are being sent from control center to substations. Now we have considered different kinds of malicious command behavior. For example, one is the command has different behavior than the normal operations, such as not a regular command. So as I said, we might have IDS in place. So if the command is not a routine command, is kind of unusual command that we generally don't do. So that might be a clear indication something is wrong, right? But if the command could be similar to the routine command, it becomes much difficult to understand whether this is actually legitimate command or actually sent by someone else. Suspicious commands for critical power component, uncommon command for opening transmission lines, and so on. Now, opening a transmission line is a big deal. Yeah, you're connecting the whole network. The command was sent by malicious user or the adversary. So again, depending on different scenario, we need to take certain actions and so on. So we capture first command behavior by using IDS. As I said, if it is unusual command, IDS can flag it easily. With the defined rules, and later command behavior is verified with the proposed scheme. So what is this scenario and scheme about? So as we said, whenever every after half an hour or so, control center sends a request called polling request to the substation, to the RTU at the substation. And the role of RTU is to then at this point of time sense, connect to the sensors. Sensor sends the current measurements, send back to the RTU, and RTU send all measurement back to control center SCADA system. Right. So whenever you receive polling request, that's part of a command. Yeah. So request is being sent. So control center sends a command to one or more control nodes, depending on how many substations we have. Each substation we assume have one RTU. As a polling request, control nodes, which is, for example, RTU, sends their measurement data to the supervising node or the control center. Now we say normally sending such commands by control center is a part of their daily routine activity. As I said, every half an hour or an hour, we need this kind of information. So if you have a smart meter, that sends generally your smart metering in every 15 minutes or every half an hour. And your utility can generate bill based on those readings. Right? Because if that system is not working, then sometimes if there's an issue, can you go back, check your smart meter, the reading, can you, there's an online portal or app where you can go log in there and you can provide what is the current reading you see in your smart meter, and so the bill can be generated. So that's another way if there are issues in the system. Okay, by the time of polling response, RTU sends periodic measurement data of different power component deployed as substation to the control center. So whatever power component we have, you have sensor that can sense those measurements and send it back. So say in real scenario, the utility either protect their communication network using VPN, which most of the companies do, or simply do not involve any protection due to a large deployment cost. Now we are talking about very large so you might have a very remote substation, right? So we are talking about a very wide network. Most of the time they may have private network because data is sensitive to them, because data is the one that will help them to make the right decision. So the question is, even in the presence of VPN network, adversary can modify measurements, data values, or commands before the starting points of VPN and substation. So you have started VPN from this device to this device. There might be possibility people can hack this device, get into the system, put some malicious data, and you end up with sending malicious data. Now when it comes to encryption or signature, the traditional typical algorithm that we've seen will not work here, because we are talking about a system that needs data quickly, right? And you want to process it. It's a very kind of multiple times in a day. So if you have a process that generates large overhead, your whole system will be too slow to handle it, right? So if we are doing something too frequently, we want this to be lightweight, as light as possible, so that the overall overheads are lower. Such a scenario involves frequent communication between supervisory and control nodes, which require an efficient and lightweight scheme. Okay. Okay, so what we did, again, we tried to come up with a scheme that is based on hash functions. So generally, whenever we develop this kind of lightweight scheme, we make sure, or we prefer to use hash function, we prefer to use XOR, and so on. And at some point, we discuss why do we use XOR, why do we use hash function, and so on. So we come up with a scheme and use a set of hash functions to generate signatures and maintain strong message integrity. So the whole point, when you send your command, along with that, you create a light signature, send it, so that in one way, quickly someone can verify it, right? One-way function is used in the scheme to announce later at the time of delivering. So we'll see that, how it works. Our signature scheme utilizes, then again, whenever you think about designing a scheme, designing a method, you always wanted to know what is available, right? So at some point, we got to know that there are multiple schemes, similar scheme people have already designed. For example, Beaver, this one and this one, there are 2-3 schemes. And we try to understand how they look like, what are their pros and cons. So for example, one of the schemes has large signing time. The other one doesn't have randomness to the input of the hash function. The third one has quite large public key size. So if you are using an algorithm which really like large public keys, that's not going to work in a way, because this will make your whole system too slow. The scheme also provides randomness to hash functions using fixed size, public key, private key. Okay. So what we did, again, we also try to understand the scenario where we are working under DNP3 protocol. Yes, again, what are the protocols that you are using for communicating between control center, substations, and so on. So you also need to take into consideration what could be the constraints when you are using a certain type of protocol. Yeah, so from protocol to protocol, the requirement might change. So you have to take into consideration while you are thinking about designing anything. Okay, so this is what we have. This is what we thought. So this is kind of typical scenario of multicasting. You got supervisory node, control center, sending commands to different RTUs, and in order to do so, what we were saying is, whenever we need to send a command, so command is being sent from control center to substation. We are sending commands with signature, with a digital signature, because that command is critical. We wanted to ensure whether only the legitimate command should be executed. If we have any doubt in a way this could be malicious command, we don't want to execute it. So you generate signature, along with signature alert message, you send that signature, and at RTU you should be able to verify it in some way. So let's say the scheme that we have come up with proposes lightweight signatures with message integrity for critical as well as non-critical commands, and alert messages such as sending open breaker command for a generator. Now, part of the routine commands, some command could be critical. As I said, if you are detaching a generator, opening a transmission line could be really critical. But there might be some other command which are kind of routine command, non-critical command, some notification messages, yeah, that we send here and there to manage things. They're not as critical for us. So what we did is, so I'll try to be as simple as possible so we can understand what's going on here. So what we did is, in our scheme, we said the control center sends a single or a set of public keys. So again, it's kind of a public key crypto system, but we are having multiple pairs of public-private key pair, right? Because they're lightweight, they're easy to crack in a way. They're not super strong algorithm, because if you do that, there will be number of large computation will be involved. So what we want, the whole point is derive lightweight system, derive lightweight keys and so on, and do this more frequently. So, in case you are compromised at any point, you can derive a new pair of keys, and so compromising the current session may not have impact on the future in a way. So, we have single, so it sends either single or a set of public, set of generated public keys. We call it PK in cipher form to the respective control center, which is your RTU. Depending on the type of communication, again, some messages needs unicast communication, some might need multicast, and some might need broadcast. I mean, mostly unicast and multicast. These public keys can also be sent to the control nodes in advance. So, obviously, they need to know in order to verify. Public keys are used to verify signatures, right? We use private key to sign, right? So, someone needs to know your public key in order to verify your signatures. Now, because utilizing shared symmetric key does not provide non-repudiation, we construct signature based on asymmetric key. So, what is non-repudiation again? What is this statement? What does it say? It says utilizing shared symmetric key does not provide non-repudiation. What does it mean? So, repudiation is the property where we say if someone has sent you a message, and you should be able to, and if you are able to decode it, you should not be able to see that you haven't gotten the message or you haven't seen the message. On the other hand, so a person has sent a message, they cannot deny that they haven't created this. And generally, this is very applicable in the case of asymmetric crypto system where you have public and private key. So, if you are signing a message with your private key, which is only known to you, if someone having your public key is able to verify your signature, it means that message was created by you. So, it's kind of a very easy and straightforward in asymmetric. But in symmetric crypto system, we said both parties having the same key, right? So, you decrypt it and you can't, there is no way that can ensure that the other person might claiming you haven't, you are the one who created this message, not me, because there is no way you could derive it. Both parties have the same key. There are algorithms and processors where we have a group keys, multiple people having the same key, and it becomes more difficult to understand who have actually created this message. So, there might be some dishonest user within your group and system, yeah, they might influence this kind of thing. And that is why most of the systems which are relying on symmetric key, they have the symmetric key more or less hard coded in the system. For example, your SIM card, your cellular network, it is based on symmetric key, it does use AES and those kind of algorithm. And one of the symmetric key is hard coded, it's in your chip. So, you cannot change it. And then based on that symmetric key, every time when you make a communication, it generates a session key and encrypt your data using that session key to send it. Yeah, if you have a Vodafone have the other key. So, Vodafone company comes with a chip, got one key, putting here, and then keeping a copy in their server. Whenever you try to connect, they can verify it. But you can't change this key. So, most of these systems where they have hard coded keys, hard coded in the system, so you can't change it. If you are able to change it, there will be chaos. People can copy the key and you have no idea who have created this message, who have sent this message. There will be too much fake content. But in asymmetric, it's easy to pick up because people have their private keys that can help them to sign their messages, and through public key you can easily verify. Right. So, in our scheme on the supervisory node, which is control center, has set of private and public keys, as the signature can only created by supervisory node. So, signature can only be created by control center and should be verified by substation or the RTU. So, what we did is very simple, is kind of a double hashing technique. So, we said we are generating some random number, we are calling them secret keys, SK1 to, I can generate number of them, and I'm doing hash of string. So, I'm passing this number to hash function and doing some double hashing and calling it kind of my signature. Now, when I do double hashing, I'm deciding which hash function I'm doing at the runtime. Yeah, so I can pre-compute this hash of this number, and I'm calling it somehow some kind of keys, secret keys. I can pass these keys to the substations in advance if like. But then in order to verify that, they need to pass this to the function that I've decided on. So it's not pre-computed, it's on the fly, so that it's very difficult for people to understand what will be those values. So for non-critical messages, you can send those values in advance, because the whole point is just to send the notification in a way. It doesn't have more kind of critical or confidential information, but for the commands, we would like to send things at runtime on the go. We were also using the key that we were using for bad data, the other part that I described. So I'll skip that. So, but what is the whole point here? What we are doing is we got the private keys S1 to Sk, Sn. We are deriving hash based on the ID of the substation that we are using, what message, what command you want to send, performing over hash function. And once you got this H, we are dividing the hash code into different strings. So we are not sending the hash code in one go, we are sending hash code in part of it. Now one of the scheme we have seen something called Shamir secret Shamir share. What it does is, if you divide a share in n parts, any t part of n can reconstruct it. So you don't need the all parts in order to reconstruct it. So as I said, the example, I got a lock where 10 people have different keys, they put it, and then lock can be unlocked, for example. If you're using this scheme, any 5 people can unlock it. So you don't need 10 people, rather maybe the 5 people can work. So maybe you can utilize the similar thing where you got the hash code, you distribute this, send it, and any few people part can reconstruct that. Yeah. And then with your signature, you're also sending kind of timestamp so that people also get to see whether the signatures are fresh or not. So you are kind of putting some threshold time. If you're receiving a message after a certain time, you're going to discard it if it is for the critical commands. Right, and similarly, so as I said, so we are dividing split H into L strings and interpret each of those parts as integer. So then what I got the hash code, and generally the hash code is in hexadecimal. I'm dividing it to different parts, and each of those parts I'm converting this hexadecimal into decimal, and then sending the decimal part out of it. Yeah. Again, they all are very light operation. They can be done on any tiny devices. Those kind of conversions, they're quite easy. And then we are doing this very frequently, so that even someone compromise one of those things, the part of the system is really safe. Yeah, that's what I said. Okay, so again, you also need to consider how long the signature can valid. So the key expiration time depends upon the frequency of the wireless transmission error. So we talk about how this wireless transmission system works. So whenever you got an error, you want to generate new key, depending on how many packets you have collected. So if somebody is monitoring, so the simple example, I'm generating a key depending on if I'm receiving a packet constantly, there's a packet drop. I'll count all the packets, pass this to a hash function, for example, and calling it a secret. As an attacker, in order to crack it or in order to generate the same kind of key, you need to track what I'm doing exactly. You need to track how many packets I've received, where's the drop, which is always not the case too. You also need synchronization in the system in order to actually understand that. So which is kind of not easy to do. Seems to be simple, but it's not easy to do. And then again, we said we want to understand what is the load profile in next half an hour and want to simulate and see how it looks like, how much time it's going to take if I'm creating signature and need to be verified, how long it will take. So if you look at this, we look into SHA-1, 256, 384. So obviously SHA-1 is kind of better in terms of performance, but then we have used combination of these to balance security versus efficiency. Right, so again we use the similar interface to send a command. So you decide on whatever command you want to send to a device, and then you are kind of recording their logs, like communication, what happening at routers, what time they have seen packets, what time this command being sent, and so on. And you creating signatures, sending along with the command. At RTU, they are kind of verifying command, verifying signature, and get to see the command whether it's legitimate or not. So that's why we are doing somehow the signature don't match. Signatures are matching in a way. We are also computing time. So for example, milliseconds or maybe 17 milliseconds or so. So it takes, in this example, it takes around 19 milliseconds to create a signature, and around same time, like 17 milliseconds to verify signature, which seems to be quite reasonable. Yeah, it's not just a second; it's just milliseconds. So it's quite quick. In a way, we can kind of do this for those kind of critical messages. We also try to understand sometimes what will be the size of the key. Do we need storage to store those keys? You know, and then always we try to compare with what people have done in the past, what capability we have for the system, and so on. So for example, we are saying verification cost. So it's a 2L plus 1, so on, where L is how you divide your string. So we are dividing the string into L substrings in a way, right? So again, this is example if kind of comparing it, what if you are using more typical signature algorithms. So we implemented RSA here. We implemented something called digital signature algorithm. There's another algorithm called elliptic curve-based digital signature algorithms, which are more typical algorithm, but they are not as fast. And in a way, we try compare with what we have. So our scheme is kind of much faster than, which says typically that these traditional signature algorithm cannot be applied because they take a lot of time for signature creation and verification. We need more storage if we want to deploy those. And if we are using this kind of idea that one we presented, will take only few milliseconds to do this kind of work. And you can easily deploy it not just on, in this scenario, you can deploy it on IoT devices and so on and so forth, right? And then the number of scenario we work around. The another scenario is typical home or residential area. So let's say you got number of homes, each home got a smart meter, and there are aggregators in between collecting your data, and they are sending this data to control center, so that control center get a sense what is the current demand in this region, what is the current supply that they can offer. At the same time, data need to be provided to billing center so that they can generate bills based on the your consumptions. So now different theories around it, whether how you go for, in a way, you're generating billing after a month. What about generating bill kind of make it more prepaid? So there are also kind of prepaid smart meter coming up where you have to, it's kind of a recharge, the way you recharge your mobile phone. Yeah, it's a very similar idea. You recharge your smart meter, use it, and then keep recharging it after a while. It's kind of a prepaid environment, but there's also postpaid where you got to see the bill every month or so. Now the question is again, if we wanted to do this same kind of thing, your control center doesn't need, again I'm talking about that in more detail, but in this typical scenario, we call this, let's say HAN, which is home area network gateway. This could be, you might have buildings, so we call it building area networks. You might have neighborhood, larger distance, we call it neighborhood, so NAN gateways, yeah, and neighboring area network. And we might be running different protocols, communication protocols, in order to send data from here and there. The same theory in a way, we are not trusting any of the entities and making sure how you enable this communication in a more secure environment. For example, you got energy providers, power generation, you got electricity in some way to your smart meter. So now what happens, how you verify information, ensuring integrity, authentication, those kind of things. You might have communication between smart meter and the gateways or the aggregators at NAND gateway. So again, this kind of information they are sending, and again those aggregators might getting data from different smart meter at the same time. So might be we need this kind of scenario where multiple smart meters sending data to aggregator is collecting them and handling in some way. And this is kind of your smart meter is sensing data from the appliances that you are using at home. So there might be a number of home appliances that you might have smart kettle, you might have microwave, television, refrigerator, washing machine, and so on and so forth. Everything is using electricity, right? So they can sense data and then processing it. Now the whole point for us is to understand the integrity, maintaining the integrity, authentication in the scenario. But there might be possibility where people say, I don't want to send this data plain text, I want to encrypt it. So we are encrypting the consumptions. So whatever smart meter is receiving encrypted data rather than the actual unit, sending it to the aggregator in the control center. And we want to process data over the encrypted network, not the normal one. Yeah, so we also think about that problem. We pick a typical smart meter. So you got a household with the smart meters. We call home area network. You got aggregators that are sending data to control center or utility. And there's also something called billing center that needs data for billing purpose. Now, in order to maintain the privacy of data, your control center or data DCO, data concentration center, they need data, but not the identity. They are interested in the number of unit consumptions. On the other hand, your billing center needs to know which household this data belongs to so that they can generate the bills. Right. So again, we were looking into, because it's a scalable system, we want to generate, we want to design an algorithm that generates lower overheads, at the same time help us maintaining the privacy as per needed. Yeah. Intermediate devices like aggregator should not be able to reveal any information. They should not be able to learn anything. And then again, talking about some general attacks that system should protect against most typical security attacks. So how we go after it? So okay, so what we did is we come up with a scheme saying our scheme is based on homomorphic encryption. What is homomorphic encryption? We talk about that. What is homomorphic encryption? Sorry? So homomorphic encryption allow you to perform computation over the encrypted data. If I wanted to know total number of units, in this particular region, and when the data is encrypted, you can still do that. You don't need to decrypt data in order to count number of units. So we go for this homomorphic, pretending that data coming from smart meter or from appliances is encrypted. And since the data would be large enough coming from large number of households, you cannot have methods where you can go and decrypt all the data and then process it. Rather, we want to apply an algorithms where data can be processed even if it is encrypted. So you can perform certain functions, not everything, but it supports some kind of functionality that you can apply. We also did something called proxy re-encryption. So as I said, we don't want to encrypt data in a way, but there are functions that can help you to do the same thing. They decrypt and encrypt at the same time. So you decrypt with one key, but then encrypt in another key, right? If let's say that 3 entity, I'm sending a data to him, and then he's passing that data to someone else. Now I'm using a key that is between this and this. I'm encrypting, sending it. This person can decrypt it, And now this person also needs to send that data to another person. So they need another key to encrypt it, and so that that person can decrypt it. Now at this place, we are using proxy re-encryption, so we are not repeating that process twice. In one go, the data will be decrypted with the key that is shared between me and him. At the same time, data will be encrypted with a key with this one. So that's why we use re-encryption. Yeah, so this kind of help us meeting the efficiency requirements and so on. Again, we go for bilinear pairing. It's one of the best property that it has. So we decided to go with bilinear pairing. And the way this looks like homomorphic encryption, where you generate keys, you perform encryption, and then you perform decryption. That's how. Okay, just skip everything. Just understand this line. So you got ciphertext. So I'm saying my data is encrypted. So let's say you have two messages encrypted over the network. So you are doing C1.C2 mod n square, n is a group, and so on. You perform decryption. So if you got two ciphertext, you are doing this calculation. This is how it come up with. It says M1 plus M2 mod n, where M is the plain text, C is the ciphertext. So you need to multiply ciphertext, perform mod n square, and the results would be same as you add both messages and perform over n. So that's how in this process, in this case, you are able to perform addition over the encrypted data. Yeah, if I have 5 different messages encrypted, if I using homomorphic encryption, I should be able to compute addition over encrypted. I would be able to see the sum. What is the sum of this? Yeah. So that's why we use homomorphic encryption. Yeah, again, the whole kind of scenario is we got public and private key crypto system where I can generate a random key, and then you generate g to the power that number, maybe my public key. So if you're generating a random number, and I'm performing, let's say g is known to everybody in the group, and if I'm performing g to the power that number, if someone who is having this g to the power s, for example, can they derive s out of it? So I generate a number x, let's call it, and I'm performing, let's say 10 to the power x, where 10 is number, everybody knows that I compute 10 to the power x, which is g or any constant number. Anybody who's having this computation, can they derive x? If they are able to do this, they will break all these algorithms. The answer is no, they cannot. Why? So this problem is called discrete logarithmic problem. I don't know if you heard about it. So for example, in the case of RSA, we were saying that we have two large prime numbers. Once you multiply them, there's no way people can factor it if they're large enough. If they are able to do so, they will crack the algorithm. They will crack the RSA. Because once you know P and Q, you know P minus 1 times P minus phi n. Once you know phi n, the algorithm is gone. In a similar way, if I'm picking a number, performing g to the power x, sending it to someone else, despite of the fact they know g to the power x, they know g, they won't be able to derive x. If they are able to do so, they can break number of algorithms, not just this one, the large number of algorithms. So there are certain mathematical principles based on we formulate those protocols. We assume that these properties are secure, they've been not broken. So, right, so in a way you, for each of the entity, you generate a number, call it a secret key, random number which is secret to individual, and then you perform public key which is g to the power x, share with people who wants to send data to you, right? And then you also have a re-encryption key, for example, g to the power b and by c, which is c minus 1, right? So you generate those keys and somehow perform re-encryption as well. So in this case, as I said, we need data. DCU needs data to compute total supply, total demand in this region, and also get a sense whether they have enough supply. If not, then they need to disconnect lines or connect new lines so that they can get more power in this region. You got billing center that needs to know individual identity so that they can also get the bill. Yeah, so that they can generate the bills. Okay. So we run this scheme reflecting in what will happen at smart meter. Again, we are creating some sort of signatures so that whenever data being sent from smart meter to aggregators to other intermediate entities, every time we are verifying signature so that we get to know that data coming from the right source and data is also been not tampered, right? And somehow at gateway, aggregator or DCU, we are kind of decrypting using homomorphic algorithm. You should be able to derive all the messages. So at DCU, we are mostly interested in get to know the total demand, right? Or the consumption unit. So if the data is encrypted, we want to perform addition over the encrypted data so that you get a sum. But for billing purpose, you need individual meter reading coming from different individual household. So you kind of reflect what happens at communication server, what happens at data consultation unit, and what happens at your billing center. So again, we are not going to detail, but there are ways by proxy re-encryption we can derive individual data from each household, and so that they can use for billing purpose. We also looking into what if some of the metering, some of the data is malicious, assuming there might be rogue smart meter or somewhere it's not working properly, or maybe there's an attacker that can inject data over the network. So how do you differentiate or identify malicious data out of it? So the very quick thing is, again, we can compare certain things in batch. Yeah. So what does this symbol, this pi, what does it do? So sometimes you have sigma as well. Yeah. What is sigma? Summation. Yeah. It's perform. If I'm saying I equals to 1 to 10, it will sum that number 10 times whatever is the values. Similarly, this is for multiplication. Yeah. So we are somehow performing some condition. We'll say while this is not equal to this, do this, right? And in between, we are using something. So this method is based on mostly what we call, the way we look for binary search tree. Have you studied that? What is that? How do we do so? Right. So the very simple principle, you always divide in half. So if you have very large problem, very large number to sort it, for example, the basic principle divide into two parts. One part, then divide. Keep dividing until you got two parts, only two elements, so that you can compare which is greater, and then keep merging all together, one part, the other part, and the whole. Yeah. It's very simple method. So that's how we are doing. We have large number of data. We're somehow performing some equation which will help me to understand which part of the data has been modified. And I can do this in batch rather than doing individual. Right? Let's say my data should be 100. If it is 101, I may divide into two half. One part might have 50, one part will have maybe 101. So I want to compare which part seems to be 101. One is 50, one is 51. So definitely 51 will have some addition to this. Then you go 51, divide it 2 far, 25, 26. Go to 26, divide into 2 half, and so on and so forth. At some point, you'll be able to say this value is different than the expected value. Yeah? Kind of similar thing that we do. And then we'll look around the performance, security, comparison, and so on. So the number of algorithms already available, kind of protocols. We look into what they are offering in terms of, are they doing prevention against attack, are they maintaining data integrity, are they offering privacy of the data as we need it at DCU, at billing centers, and so on. Try understand what are the different functions that we are using, and what will be the computation look like, how many times we are using them in the whole process, and what kind of computation they generate. So in this case, we are using random numbers, which are very, very efficient. You can generate in few milliseconds, not a problem. Exponentiation, that takes a while sometimes. Multiplication are reasonable. Pairing, maybe a bit. XOR, hashing, alpha, they all are very efficient. Yeah. So you can use them as many times as you want. They're very, very lightweight. So most of these protocols, you see, they are relying on hash functions, XORing, and so on, and less relying on more. We always use pairing, and multiplication, exponential whenever we need them. But if there's a process, we can do this with the XOR. We'll prefer to do so rather than utilizing more typical functions, because XOR hashing are very, very efficient functions in terms of computation. Yeah, so you have to kind of thought about it, what function I should be using in order to make it lightweight. The different ways of developing a system, developing an algorithm, but then what will be the what should be the combination that will result into least computational cost, right? So that I can deploy it on devices that do not have enough computational power. Yeah, some kind of comparison, and then we also look around computational overhead, execution time, how much time it takes. So we consider like what we have a 200 smart meter that we need to process data from 400, 600, 1000, and how long it takes. So the time in millisecond, it just take roughly 2 point something milliseconds to process data around 1000 substations, 1000 smart meters. You know, so we also want to develop this kind of algorithm which are scalable in nature. As an operator, if I have 2 minutes, probably I can handle 10 times of 1000 in 10 different areas where they have 1000 household. So we want to develop these kind of algorithms which are really scalable, lightweight, low computational. Yeah, they're easy to handle, and we can process them in batch. Maybe the last slide, I guess, before we go for another break, is NIST also talk about privacy concerns. So as I said, now researchers are also doing this work. We were working around encrypted data. Yeah, the whole theory around it, once you encrypt your data, no one can capture it. We are secure in terms of privacy of data. So so people have come up with some work based on machine learning and so on. And they processed data in such a way they were able to identify certain equipment, certain appliances that you are at home. Yeah. And in a way, operator can also get a sense out of it. For example, if you're living alone in a household, you go to work from maybe 8 a.m. until 8 p.m. Yeah, you come at home 8 p.m. until whatever. By looking at your usage pattern, people can get a sense what time you are at home. From daytime, there's no consumption or very less consumption, but suddenly there's a spike. People get to see now someone in the room. Now, this is a very simplistic example, but there are examples where data, even if your data is encrypted, there are algorithms that can process and get a sense that this data seems to meet this appliances. By looking at the usage of energy consumption, they can predict, even the data is encrypted, you have a kettle at your home, you have, fridge up, maybe this watt, and so on and so forth. So research has been like going crazy. People are developing those kind of solutions that can crack existing solutions. So it's kind of a continuous process in a way where you always need to be ahead from the attackers, from your competitors who want to break this kind of system. Right, so I mean, if you Google it, you come across some of the papers where you can look around those tables and figures where people say. And people have literally able to identify that you have this kind of appliance at your home based on the consumptions, even when the data is encrypted. Right, so it has emerged new challenges, new privacy challenges. So that simply means encrypting data may not be enough. So you start thinking, can I introduce noise to it? Can I do this and that, to make it more, again. So yeah, so we just wanted to do that. Let's have another break.